Okay, I'm gonna be dead honest. I hate friction problems. I'm like having to force myself to do these because friction problems are awful. And I also don't like blocky friction problems and everything's stupid. Okay, so there's a thingy and a frictionless pulley and a block and it's doing things and it makes me sad. So I'm gonna do this block at the bottom and a free body diagram of the block at the top. And I want to move the blocks at a constant speed. And the kinetic friction between all surfaces is 0.4. So they each have a tension. So that tension is the same as that tension. And then the top one is 2 kilos. So 2 times 9, oops, that's not a 9, 9.81, bleh, 1962. Okay, this is T, 1962. And the bottom one is 4 times 9.81. I'm avoiding having to think right now. 39.24. 39.24. And then this is like on the surface here, and this has a surface here, and this has a surface here. So there's a normal from, I'm going to call this A and this one B. There's a normal to the ground, and then this one has a normal between A and B, and this normal A and B is the equal and opposite reaction force. So like if I took these two like that, and I combined them, that normal force would go away, but the two weights, the two tensions, and the normal force on the ground would still be there. Oh, and the P off to the left. Okay. So that's how I know I've done it right, but I'm not quite done yet. But just for the purposes of that normal force, making sure I've got the arrows drawn the right way, is if I combine them, they're going to go away, and everything else is still there. There goes my cuckoo clock again. This is the set of videos, the cuckoo clock. Okay, and now I'm going to be pulling it to the left, so that's nice. So I know that this one is going this way, and this one is going this way, which means the friction is opposing the motion, and the friction is opposing, ooh, this is important. The friction is opposing this motion between the ground, and then this friction is opposing the motion between A and B. And here's the thing. This is the one I would forget if I was a student, because I'm like, well, clearly there's a friction here. But if I put them together, and I just kind of took a picture of them as a system, right? Wherever it's touching, those two frictions would cancel each other out for the purposes of an instantaneous picture. So this FAB goes to the left because it is the opposite of that AB. Does that make sense? So if I closed these two together, the NABs would cancel out and the FABs would cancel out. Okay, so this is a little weird. And they just kind of throw this at you. But the normal force between those two, and that's how that FAB would be labeled, is the frictional force AB, since it does say it's moving, would be the kinetic force times NAB, whereas a frictional force for the ground would be mu K times NG. Okay, does that kind of make sense where we're going with this? So this is a kind of a complicated problem, but it's something that you really need to understand going forward. Okay, so hopefully that's something. And again, just if it helps, and I don't know why this helps me, it just does. The idea is if I put these together, the two normals cancel out, and the two touching normals cancel out, and the two touching frictions should cancel out. That's how I know I have them in the right direction. Okay, so now I can do math. And that's the whole reason we're here to begin with, math. Okay, So I'm going to do the sum of the forces in the y first. And I know that block B is not flying off into the sun, so negative 1962 plus NAB is equal to the mass of, what did I call this? A. Did I call that A? Did I already forget? Yeah, okay, this is A and this is B. So this would be the mass of A times the acceleration in the y direction of A, which I know is to be 0. So NAB is 19.1662. NAB is 1962. Good? Good. Okay, so because it's kinetic, I can use FAB equals mu K NAB, and mu is 0.4. FAB equals 0.4 times 1962. Okay, 0.4 times 1962, 7848. Okay, so now I know the sum of the forces in the x direction on this dude are force of friction going back, tension going forward, and the mass of A times some unknown acceleration to the right. Okay, so I know the FAB, but I don't know T and I don't know AY, so I have two unknowns here. I guess I can label the mass of A was what, 2? The mass of A was 2, and this one was 7848, so I guess I can come over here and I'll finish this a little bit. So I have negative negative 7848 plus T equals 2AY. So negative 2AY plus T equals 7848. Okay, so I'm going to save this for later and come back to it. All right, now let's look at this for B. Whew. All right, this is more of a problem than you think it's going to be. I have no idea how the book's solving it, by the way. Sum of the forces in the y direction. Now, there's a negative NAB. There is a negative 39.24, and there's a positive NG, and this is equal to mass times acceleration in the, oh dang, I wrote this as a Y and nobody said anything. AX, X, X. So that's what you get. Okay, MAY, but I know that the acceleration in the Y direction is 0. So, and I do know what NAB is. NAB is negative 1962 minus 3924 equals negative NG. So NG equals 1962, which really makes sense because it's just the weight of the two things added together. And nothing else weird is happening. So 5886. 5886, like that. Okay, now, so if I look at the sum of the forces in the x direction now, I can't decide how I want to do this. I'm just going to do it the normal way. Okay, so I have minus P plus T plus FAB plus FFG equals mass of B times the acceleration in the x direction. Now, the problem is I've done something weird here, and my acceleration is actually in the negative direction. So what I could have said is I could have said this is the acceleration of A in the x direction, and this is the acceleration of B in the x direction. Okay? But I can tell by looking that, say, A in the x direction is the opposite of A in the y direction. I mean, A in the, for the B, does that make sense? A, X, A, that's what I'm trying to say. That's true. And so basically, so that I have, instead of having two different variables, instead of writing this here, I could write minus A sub X sub A. Okay? If that is confusing to you, you deeply, deeply don't like it. The other thing that I was thinking about doing is saying, well, since acceleration is this way, that way's positive, in which case I pretend that I never even thought about the fact that there could be multiple accelerations, which really isn't a great idea either. But now I could do some of the forces in the x where this way is positive. So I'd have negative p, plus p minus f ab minus f fg minus t, and that equals max times acceleration in the x. So you can also do it that way if that works better for your brain. But I feel obliged to do it the other way, just to show that there are two accelerations and that we can go and say, okay, well, this one acceleration is the same thing as the other acceleration, but in the opposite direction. So that's theoretically what we were supposed to do. Okay, so P is the thing we don't know, or do we know what P is? Okay, it's pulled to the left by P. Okay, so P. Whoa, that's giant. So pulled to the left by P plus tension plus FAB, which I already found somewhere was 78.48, plus FFG, which is going to be 0.4, because that's that coefficient of static friction, right? 0.4? Yeah. Times 58.86. My handwriting is messy today. So 0.4 times this. Actually, I think I'm about to do something silly, or realize that I could have done something earlier. FFG is 23.5. FFG is 23.5. Okay, plus 23.5 equals the mass of B, which was 4 kilograms? Yeah. Times negative acceleration of x in the a direction. Okay, so now I have 3 unknowns, which means I did something wrong, which means I need to go read the problem again, right? Because I have t, a sub x, and p. Okay, so now I'm going to go read the problem. When all else fails, read the problem. Okay, 2 sliding blocks are attached by a massless spring wrapped around a frictionless pulley. When the bottom is pulled to the left by a constant force, the top blah 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 slides to the right. Find the magnitude of the force necessary to move the blocks at a, there you go, constant speed. So if the speed is constant, acceleration is 0. That's pretty lame. So because acceleration is constant, so I went to all that discussion about acceleration just for acceleration to turn out to be 0. So now the tension is just straight up, 78.48. And there's the dog. There's a lot of dog. Okay, so 78.48. Where did that 78.48 even come from anymore? I don't even know. Come here, chicken. Oh. Oh, man. 7.848. I'm going to have to go make an actual note of that. 0.848. So everything is off here by something, isn't it? Because clearly I can't math. Whoops. Okay, so let's just pretend I am not terrible at math. 7.848, 7.848, and 23.4. This is what happens whenever I went to try to find the previous number, and that number didn't exist. Plus this, plus this, so 39.24, so P equals, I already forgot, 39.24 newtons. Is that right? Please let that be right. Please let that be right. Yay! I did science! Okay, so N2, what is N2 supposed to be? Oh, it must be that thing over there that I didn't care about. Okay, so aside from the fact I can't read my calculator or the problem, this is how you would go about solving that problem. So there's actually potentially a lot more into this. So if it was accelerating or if you weren't sure which direction, I mean, in this case, it's obvious you're pulling, or if you had multiple pulleys and the accelerations aren't the same, it's just a really interesting kind of problem. So there you go.